Today, we are going to talk about the so-called birthday paradox. It is known as a paradox because the answer that we are going to give to our problem is counterintuitive, and I would say even surprising. Let's first start with the birthday problem. Assume we have n people, at least two, of course. We would like to know the probability that at least two of them will have a birthday on the same day. This is known as the birthday problem. Most importantly, this leads to the following question, the birthday paradox. What is the smallest integer n such that the probability that at least two people from a set of n people celebrate a birthday on the same day is greater than 50%? We are going to prove this in a very elementary way, without introducing any big theory. Before we proceed, let's just agree that we are going to consider years with 365 days. That will be easier for us. Also, it should be clear to everybody that if there are 366 people, then our problems have an easy answer. Because there are more people than days, then obviously there are at least two people sharing their birthday. Step by step, slowly but not too slowly, we are going to reply to the first question. Remember that we want to know the probability that at least two people in a group of n people are sharing their birthday. When we deal with this kind of at least question, it is often advisable to first face the opposite question. What is the probability that nobody will have a birthday on the same day? So let's start with the easiest case, the case n equal to 2. In this case, the answer is trivial, 364 over 365, which corresponds to more or less 99.7%. The reason is the following. Let's call A and B those two people. Let's fix the birthday of A. For instance, it can be January the 1st. Then there are 364 chances out of 365 that the birthday of B will be on a different day. The case n equal to 3 is pretty much the same. The answer is 364 over 365 times 363 over 365, which is more or less 99.2%. Now we are going to explain this. The proof is more or less the same as before. Let's call A, B, and C those three people. Assume A was born on January the 1st. Then there are 364 chances out of 365 that the birthday of B is on a different day. Assume now B was born on January the 2nd, for example. Then there are 363 chances out of 365 that the birthday of C is neither January the 1st nor January the 2nd, and this concludes the proof. As for n equal to 4, we go on in a similar way. We just need to add an extra person. Then the result is 364 over 365 times 363 over 365 times 362 over 365, which is more or less 98.4%. Okay, now we understood how to proceed and we go on like this. So for n equal to 5, we clearly have to add an extra person, and we have the following result. 364 over 365 times 363 over 365 times 362 over 365 times 361 over 365, and that's it, which is more or less 97.3%. Fine. If now we want to generalize to any n, we simply need to multiply together n minus 1 elements. So the result will be 364 over 365 times 363 over 365 times 362 over 365, and we go on like this until the last term, which is 365 minus n plus 1 over 365. Please notice that we really have n minus 1 factors. Now, this is equal, be very careful, to 364 factorial over 365 minus n factorial. And all this is the numerator of the previous expression. And the denominator should be multiplied by 365 to the n minus 1, which corresponds to the denominator of the previous expression. Now we come back to the original question. Remember that we want to know the probability that at least 2 people will have a birthday on the same day in a group made of n people. In this case, we simply need to do 1 minus what we obtained in the previous slides. That means 1 minus 364 factorial over 365 minus n factorial times 365 to the power of n minus 1. This is our final answer to the first question that we called the birthday problem. Let's call this function Pn. It's clearly a function of the number n of people. If we want to reply to our second question, the birthday paradox, then we simply need to evaluate the function Pn for several number n until we find a value which is greater than 0.5, which corresponds to 50%. Let's start with P2, which corresponds to more or less 0.8%. Then we go with P3, which is more or less 1.4%. Then the percentage, we notice that is constantly increasing. Now we do a big jump until P22, which is very close to 50%, but not yet. It's actually 47.6%. The next step is P23, which finally gives 50.7%, which is actually greater than 50%. So yes, we made it. In a group of 23 people, it is more likely that at least 2 people are sharing a birthday than the opposite. That means that nobody is sharing a birthday. You should try it with your colleagues, your friends, your students, your schoolmates. And that's it for today. Thank you very much for watching. Please don't forget to like, comment, and subscribe. Thank you again. Bye.